2. Now for cosine, when I make my table of values, I'm going to use my quadrantals, 0, pi over 2, pi, and 3 pi over 2, but I'm also going to include my pi over 3s, because that's cosine of pi over 3s gives me something really nice. So let's go ahead and make our table. Theta and r. So theta, start with 0. I go 3 minus, you can do this in your head. What's the cosine of 0? 1. That gives me 2. So at 0, I'm facing 0. I'm facing 0. As remember, this is 0, 2, 0 radians, right? So we face 0, go out 2. 1, 2. Put a point there. Now, pick my pi over 3. Pi over 3. 3 minus the cosine of pi over 3. Well, that's a half. So this is 3 minus a half, which is, oh, yuck, 2.5. So I'm facing pi over 3. I got 1, 2.5. Sweeping. All right. If I pick pi over 2, don't pick pi over 6. It's not a nice number. I go 3 minus the cosine of pi over 2. Well, the cosine of pi over 2 is just 0. So 3 minus 0, which is 3. So we go up 1, 2, 3. Not going to be perfect, but that kind of looks like it right there. Next, my next pi over 3, 2 pi over 3. So I go 3 minus the cosine of 2 pi over 3. Cosine's negative. This is 3 minus a negative a half. So what happens here? This gives me 3.5. So at 5 pi over 3, go up 1, 2, 3.5. So it's kind of like it's still kind of going here. Look at that. It's still kind of getting bigger. Okay? Pick pi. 3 minus the cosine of pi. Well, pi is just negative 1. 3 minus the negative 1 is 4. So at pi, I go at 4. 1, 2, 3, 4. Pick 4 pi over 3. 3 minus the cosine of 4 pi over 3 becomes 3 minus a negative 1/2. That's negative 1/2. Whoops. So I get 3.5 again. 1, 2, 3.5. And remember, they are symmetric. It almost looks like a circle, but it's not. We'll talk about what happens here at the end, okay? So pick 3 pi over 2. 3 minus the cosine of 3 pi over 2. Well, cosine of 3 pi over 2 is 0, so that's just 3. 1, 2, 3. And pick, let's see here, 5 pi over 3. Three minus the cosine of 5 pi over 3. That becomes 3 minus 1/2 becomes, what's that, 2.5. So what's that? There we are. 1, 2.5. There we go. And if we pick 2 pi, that's the same as 0. If we pick 2 pi, that becomes the same as 0, which is just 2. That's going to put me back where I started. Now, we didn't talk about this, but really what happens is it kind of comes out a little bit more. It makes like a little bump. It's almost like our cardioid. This is called the lima bean, the bean. It kind of goes up, and it kind of goes down, and then it comes back out again. It makes a little bit of a bump here at the end. So if it doesn't touch the origin, it's always going to make a bump. It's kind of a line. This is actually called a lemmason. This is the actual definition of a lemmason. And a lemmason is a French word for, you guessed it, bean. These look like beans right there, like a kidney bean. Does that make sense? We have a little bump there. We'll talk more about that in class. So this makes what's called a bean. It's a special name. All right, so I have another example right here for you, and I would like you to try this one. What do you think it's going to be? Okay, we'll probably answer in a second, but go ahead and try this one here, and we'll go over that in class on Monday. But let's take a look down here. Rules for lemmicons, or lemmasons. Miss Noon always gets mad at me because I say lemmicons. I'm German. I'm not wimpy French. All right, anyway, so to do a lemmason, this is the rule. It's R equals A plus or minus B cosine theta. Now, if it's cosine, it's going to be symmetric on the x-axis. In other words, like a cardioid, it's going to always be along the x-axis, like so. If it's A plus or minus B sine of theta, it's going to be symmetric on the y-axis. Like I might just draw like a normal limacon. There we go. Makes like a little bit of a bean right there, okay? Now, if A equals B. Now, here's what I want you guys to think about. If A equals B, if A equals B, at some point, these are going to cancel each other out because cosine can be negative. So it'll be like A minus B at some point. So my radius at some point has to be 0. At some time, R equals 0 because of the values of cosine. Therefore, this will always go through the pole. This way, this will go through the pole. Therefore, this will always be a cardioid. This will make a cardioid. Okay? That's our card. So if A equals B, that's our cardioid. So same thing here. This will always be a cardioid, just centered around here. Okay? That's what this will look like. Remember, this is my cardioid. A cardioid goes through the pole and touches at the pole itself. Now, if A is less than B, now think about this. If A is less than B, then what's going to happen, and this is an example, like let's take a look over here, where A is less than B, like right over here. If A is less than B, just like example number 3 over here, we get our loop. So if A is less than B, not only will it go through the pole, it's going to go past it. If A is less than B, at some time, R is less than 0. R becomes negative. Therefore, this forms a loop. Therefore, this forms a loop. A loopy limacon. A looped limacon. And something looks like this. So it might go wee. Something like that. It'll form a loop. So this will be our looped one, just along the y-axis. If A is greater than B, well, let's take a look if A is greater than B. Now, if A is greater than B, we have a problem like so. A is greater than B, well, let's take a look at what happened. It doesn't go through the origin. It doesn't go through the origin here. So if it doesn't go through the origin, or the pole, this will be our bean. Okay? Does not touch, this will not touch the pole. Does not touch the pole. Therefore, this will be just our normal, everyday, whoops, let me erase that. This will be our normal, everyday limacon, or our bean. This is our limacon, our bean. Okay? So if I were to look at this one, it might, it'll get closest here. So it'll look something like so. And there's our graph. All right, so we'll take a look at these tomorrow. Make sure you try these examples up here, okay? This is very easy to do, but you got to practice, especially with the tables. I'll talk to you guys tomorrow. Bye.